Mr. Burke. I'm here to reassess a standard 4.2 that I can apply Young's modulus in both macroscopic and microscopic forms to solve problems. I last missed it on quiz 5.1. Okay, so first what I did was I applied Young's modulus. Young's modulus is stress over strain, which is equal to the tension force over the area. O divided by the strain, which is delta L over the change in length over the length of the wire. And what I got was that the change in length of the wire was going to be equal to the stress times would be equal to the stress on the wire times the length of the wire over Young's modulus. So next what I did was I figured out that I realized that I was given Young's modulus and the length of the wire, so the only two things I needed to calculate were the tension force and were the area. So I did that by creating a free body diagram, and because the total force on the system is 0, and that the momentum is 0, I knew that the tension force must be the opposite of the gravitational force, because there were no other forces in the system. And so doing that, the tension force is equal to the opposite of the gravitational force. I found that the tension force was equal to 98 newtons, so that was good, so I kept that in my back pocket. Next, to find the area, I simply divided the diameter by 2 into the area of a circle, which is pi r squared, and I found that the area was 9/4 pi millimeter squared. Here's where I had to be really careful, because 1,000 millimeters squared is not the same as 1 meter squared. So what I did was I squared the conversion 1 millimeter over 1,000 millimeters, 1 meter over 1,000 millimeters, and I found that 1 meter squared was the equivalent of 1,000 squared millimeters squared. So using these two tools, I went back in for step number 4, and I simply substituted the tension force and the area into my equation for L, making sure that I did that important conversion. Then, after that substitution, using GlowScript, I found that the change in the length of the wire was 0.0002 meters, or 0.2 millimeters. Next up, I did a simple unit check, newtons times meters over millimeter squared times meter squared over millimeter squared times newtons over meter squared essentially boils down to newtons over newtons times meters, which is meters. Finally, the reason why I did this question is that it asks what I think is a really thought-provoking question, which is, why is it a good idea to simply assume/pretend that the wire doesn't stretch at all? And as we can see, 0.0002 meters, really, really small, especially in proportion to the system. Indeed, 0.0002 meters over the change in the length of the wire over the actual length in the wire is just 2/30,000ths of a meter, which is quite small. i.e., it's much easier to assume that the wire simply doesn't stretch at all. Thank you for listening. Have a good evening.